In this video, we'll discuss the interpretations of the derivative in the context of a real-world problem. So I went on a biking trip, and I tried to capture my total distance over the time. So this green graph here describes my total biking distance in miles over the time in hours. Well, let's say f of x is the total distance function with respect to x, time in hours. Well, using this distance function, can I explore my speed at a certain time during this trip? Let's explore it. So let's keep in mind that the ratio of the distance traveled over a tiny time interval, right, give me a good idea of my instantaneous velocity at a time. So then if f of x is the total travel distance in miles, then f prime of x is the derivative of f of x, and it would tell me the velocity in the unit of mile per hour, my velocity, my speed at a certain time. So for example, if we look at the point when t equals to x equals to 1, right at the first hour, then look at this graph, right? I know that I have a coordinate 1, 5, which means f of 1 equals to 5 in miles. That tells me that the total distance, my biking total distance right at the first hours is 5 miles. So then my question is, so what was my speed at the time? So what is the instantaneous rate of change of the total distance, which is translated to the velocity right at the first hour? So in order to find this, find the answer, again, we know that we want to construct a tangent line to this point, 1, 5, and I need to find the slope of the tangent line. So I have to find another point on the line, which is 0, 2. And I use the slope formula to find the slope of this tangent line, which is 3, which will tell me the f prime of 1 equals to 3. Okay, so f prime of 1 is a value of the derivative of the function f when x equals to 1. And in this case, it's equal to 3 miles per hour. And if I want to translate this result, I would say that because 3 is a positive number, and you see you have a positive slope, so that means the total travel distance is increasing at that point, at the first hour, and at the speed of 3 miles per hour. So instantaneous rate of change of my travel distance at the first right hour, the right first hour, is 3 miles. So related to the same example, we can discuss higher derivatives of a function. So we have the first derivative, we can have the second derivative, which is the derivative of the first derivative, and we can have the nth derivative of the functions. You can use the different notations for the derivative, dy dx, d squared y dx squared, dny dxn. So if y is equals to f of x, then you can use different notations for the derivative. So back to the same example, we have f of x is the total travel distance in miles. F prime of x, which is the purple curve, is tell you the instantaneous rate of change of the travel distance, and this is the velocity function or the unit of miles per hour. And then f double prime of x, the second derivative of f of x, is the instantaneous rate of change of the velocity which is the derivative of the first derivative, and it's an acceleration function, and with a unit of miles per hour squared. So you can see the relation between the first derivative and the second derivative with the original functions if you have a travel distance, if f of x is a total travel distance function. So you have a function that describes the distance. You can find the velocity at a certain point by finding the first derivative, and you can find the acceleration at a certain point by finding the second derivative of a function. So in this case, the travel distance is an exponential function. The first derivative is also an exponential function, and the second derivative is also an exponential function.